In any of the mechanism, when the relative motion takes place between the links at any given interval of time, the input crank and output follower changes its position is called precision position. Here we can see the 4-bar mechanism in which this is the input crank and this is the output follower. At given interval of time, the input crank changes its position from A to A1, A1 to A2 and A2 to A3. Similarly, the output follower changes the position from B to B1, B1 to B2 and B2 to B3 respectively. The angle between the positions at the input crank between A to A1 is Xi1, A1 to A2 is Xi2, A2 to A3 is Xi3. Similarly, the angle between the positions at the output follower between B to B1 is Phi1, B1 to B2 is Phi2, B2 to B3 is Phi3. As we have derived the Fredenstein equation for 4-bar mechanism, so this is the Fredenstein's equation for 4-bar mechanism. So this equation we have derived with respect to input crank angle and output follower angle. We call it as equation number 3. Here, with respect to input crank angle such as Xi1, Xi2, Xi3 and output follower angles such as Phi1, Phi2, Phi3, we can rewrite the Fredenstein equation for 4-bar mechanism with respect to Xi1, Phi1 is cos of Xi1 minus Phi1 is equals to K3 plus K1 into cos Phi1 minus K2 into cos Psi1. With respect to Xi2, Phi2, cos of Xi2 minus Phi2 is equals to K3 plus K1 into cos Phi2 minus K2 into cos Xi2. With respect to Xi3 and Phi3, cos of Xi3 minus Phi3 is equals to K3 plus K1 into cos Phi3 minus K2 into cos Phi3. Using this equation, we can determine the length of the links in the given problem. Here, we can see the problem on 4-bar mechanism in which the input crank angles are 30 degree, 50 degree and 80 degree and output follower angles 0 degree, 30 degree and 60 degree. The given data in the form of Xi1 is equals to 30 degree, Xi2 is equals to 50 degree, Xi3 is equals to 80 degree, Phi1 equals 0 degree, Phi2 equals 30 degree, Phi3 equals 60 degree. Using Fredenstein equations with respect to Xi1 and Phi1, Xi1 angle is 30 degree, Phi1 angle is 0 degree. Substitute in this equation and solve this equation, then simplify the equation, then we get K1 minus K2 into 0.8660 plus K3 minus 0.8660 is equals to 0. Call it as equation number 1. Next, with respect to Xi2, phi2, substitute the value, solve the equation, then rewrite k1 into 0.8660 minus k2 into 0.6427 plus k3 minus 0.9396 is equals to 0. Call it as equation number 2. Similarly, with respect to xi3 and phi3, so xi3 value is 80 degree, phi3 value is 60 degree. Substituting this equation, solve the equation, then rewrite k1 into 0.5 minus k2 into 0.1736 plus k3 minus 0.9396 is equals to 0. Call it as equation number 3. To find the values of k1, k2, k3, solve the equations 1, 2, 3 using calci. Ultimately, the value of k1 is 1.8298. The value of k2 is equals to 1.4276. The value of k3 is equals to 0.2726. Keep these values in positive sign. After finding the values of k1, k2 and k3, so we know the formulas for k1. k1 equals L1 by L2, k2 equals L1 by L4, k3 equals L2 square plus L1 square plus L4 square minus L3 square divided by 2 into L2 into L4. Here the value of L1, the L1 nothing but it is the length of the frame or length of the fixed link. Here we have to assume this value. If we assume the value of L1 as 1 unit, then in equation k1 equals L1 by L2, already we know the value of k1 and the value of L1 is 1 unit, then easily we can determine L2. The value of L2 is equals to 0.5465 unit. Similarly, in k2 equation, from this L4 is equals to 0.7004 unit. Then in k3 equation, we know the value of k3, we know the value of L2 square, L1 square, L4 square, L2 value, L4 value. Substitute all these known values, then simplify the equation. Then we get the value of L3 equals positive sign of 1.2571 unit. Like this, we can determine the length of the links in the given 4-bar mechanism. Generally, the mechanisms are designed to obtain the required motion at the output member. The required motion at the output member may be in the form of rotation, oscillation, or reciprocating motion. The motion of the output member always it is the function of input link motion. Here x nothing but it is the motion of the input crank or in the form of crank angle. Y is the motion of the output member. In any of the mechanism, y always it is the function of x. Chebychev spacing. Chebychev spacing is one of the method to determine the accurate precision positions in the given mechanism at the input and at the output member. Here we can see the Chebychev equation which is used to determine the accurate precision positions at the input and at the output member in the given mechanism. x suffix j is equals to 1 by 2 of x n plus 1 plus x naught minus 1 by 2 of x n plus 1 minus x naught into cos of 2 into j minus 1 into pi divided by 2 into n. In this equation, j nothing but the number of precision positions. It can vary from 1 to n. X suffix n plus 1 nothing but it is the final position of the input crank. X suffix naught nothing but initial position of the input crank. N nothing but it is the total number of given precision positions. Here we can see one of the example on Chebychev spacing. According to this example, the function of the mechanism is given, that is y equals x to the power 0.8 and x nothing but position of the input crank. It varies from 1 to 3. Between 1 to 3 we have to find 3 precision positions. According to the given data, the function of the mechanism y equals x to the power 0.8. X naught is the initial position of the crank is equals to 1. X n plus 1 is the final position of the crank is equal to 3. N nothing but the total number of given precision position, that is 3. With reference to this, j varies like 1, 2 and 3. We know that Chebychev equation, this is the Chebychev equation. Throughout this equation, the value of xn plus 1, x naught and the value of n are constant. Throughout this equation, the variable term is j, and at here, if we consider j equals 1, substitute in this equation x suffix 1 nothing but this is the first precision position of the input crank. Then the value of xn plus 1 is 3, x naught is 1, then j nothing but 1, n value is 3. Under radians mode, simplify this equation, then we get x1 is equals to 1.134. Similarly, for second precision position, j is equals to 2. Substitute the values. Here j is equals to 2. Under radians mode, simplify the equation, then we get x2 is equals to 2. Similarly, xx suffix 3, this is the third precision position. The j is equals to 3. Under radians mode, simplify the equation, then we get x3 equals 2.866. Corresponding to the values of x1, x2, x3, the values of y1, y2, y3 is given by y suffix 1 is equals to x suffix 1 to the power of 0.8. We know the value of x1, that is 1.134 to the power of 0.8. Simplify, then we get 1.1058. Similarly, y2 is equals to x2 to the power of 0.8. Substitute the value, simplify, we get 1.741. Similarly, y3 equals x3 to the power of 0.8. Substitute the value, then simplify, then we get the value of y3 is equals to 2.321. Like this, can determine the accurate precision positions at the input crank and at the output followers.